There are a few seats left in the front. Please come and sit in the front rows. Okay, how are you doing tonight? Good? It's a nice sunny day. It's great to have you here. I see a lot of familiar faces, and so it's great to see you again. We're like a family now. I feel like I know a lot of you. My name is Pashu Christensen. I'm the Marketing and Partnership Manager for the Hive, and I have the pleasure to manage the Hive think tank and to meet great people such as Michael, who's going to be presenting tonight, many thought leaders, and I get to meet you all as well. So you must know about the Hive think tank. It's a group of practitioners, data scientists, thought leaders, designers, all focused on big data. We host events every week in the South Bay in San Francisco. Tonight at Pivotal Labs, we are lucky enough to get this amazing space. They just opened this office a few months back, so thank you for having us. There are a few events coming up. We don't have any events those 2 coming weeks. This doesn't mean you are off duty. I would love for you to spread the word, invite your friends, your colleagues, your network to join us next month. So we have 3 upcoming events in May. The first one will be on May 2nd, Wednesday evening, on digital strategies for retail. This is going to be hosted in the city at General Assembly. And then we'll have 2 other ones, one on May 21st, the other one on May 28th. The one on May 21st is going to be a tech talk, and the one on May 28th is going to be a panel discussion on connected cars. So I hope to see you there. And I would like to thank our sponsors as well, and Pivotal Labs for being an in-kind sponsor tonight. And we have a few other sponsors such as Microsoft, Dell, IBM, and Perrisquis. Thank you so much. And I'm going to give the microphone to TM Ravi. He's the founder of the Hive. Thank you.
Thank you, Pashu. Thanks to Pivotal for hosting us here. I think many of you have been here before, so you know the Hive. We do 3 things. We incubate companies, we fund companies, and we have a think tank that Pashu just talked about. All our companies are in the big data space. We have a whole team of people who are in the Hive who help on the incubation and funding side. They include some technology people that many of you know, a CTO and a data scientist in residence. One of our companies went public 2 weeks ago, Rubicon Project. It was an outstanding outcome for my partner. We are focused in the big data space. There's a lot of different things you can do. So we are very focused on the applications and the use cases of data. So we have a perspective which is that there is a lot of activity going on in open source. There's a lot of technologies being built by the large vendors like SAP, Oracle, IBM, Microsoft, and so forth. So we felt that, and of course you have the cloud, you have commoditization of server and storage. So we felt that the real value in the space is around data-driven applications, either sort of line of business process applications or vertical applications. And so we are in the business of building companies. So we are looking for entrepreneurs in residence as well as entrepreneurs in security and fraud detection, Internet of Things. We're looking for engineers with Spark, Hadoop experience. So if you have any of that, we'd really appreciate if you can reach out to us. The think tank is sponsored by a number of great partners as well as in-kind partners. So reach out go to our website and click on the links and so be a part of the conversation today. So our hashtag is Hive Data. So get on Twitter and of course follow us on Twitter and Facebook. So with that, I'm pleased to welcome Michael Kanawar of LinkedIn. Michael is, Mike, I guess, is a PhD with background in complex system analysis and focused on information propagation in social networks. And I guess that's why he works at LinkedIn. And so we're excited to have you join us today.
This is still playing your music. I am Mike Conover, and I do study all of the things you just talked about. So I am a data scientist at LinkedIn, where we build machine learning workflows that leverage the behavioral relationships of hundreds of millions of people to connect the world's professionals to make them more successful and productive. My background is in a field called complex systems analysis. And a complex system is one whose behavior in the aggregate is different from and not characteristic of the individual components of the system. And so when you hold in your mind the picture of a very large flock of birds or a school of fish, and the way that it moves with this collective purpose, you see this, and one is able to detect this hidden structure shimmering beneath the surface of so many systems. And the eyes are so uniquely able to discern structure in a way that is not accessible to numerical or statistical analysis. You could consider, for example, the venous structure of this leaf. There's undoubtedly a statistic that describes the fractal branching pattern. Could you turn this down just a little bit? Turn it up? Oh, let's get after it. All right. Let's do this. All right. Well, so the fractal branching pattern characteristic of this leaf could be summarized with an individual statistic, but knowing that number, which could be communicated in just a few bytes of information, is very different from seeing the thing itself. And so many systems are characterized by this higher order structure that is not characterized by the individual components. And so when we interact with technology, we create this digital trace data that allows us to study human systems from this faraway perspective. And we can take a lens on society in the way that we might study the cell. And so here we have a visualization that represents traffic flows through Lisbon, Portugal. And this is information taken off of GPS units in taxi cabs. And the breadth of the line corresponds to the volume of the traffic flow along that thoroughfare. And its color represents the speed at which the cabs are traveling. And in the same way that having a point estimate for the fractal degree of this leaf would not tell you much about the structure of the leaf itself, individual data points coming off of intersections are very, it's thin soup with respect to urban planning and understanding how traffic is actually flowing through a metropolis like this one. And so when we are undertaking this enterprise of machine learning or data science, it is so useful to visualize the data that we have under study in order to understand its high-dimensional structure and its high-dimensional texture. And so this talk will be structured along a couple different primary pieces. We'll talk about the role of information visualization with respect to hypothesis generation, feature development, model evaluation, and then finally workflow management and how we use tooling that gives us eyes on machine learning workflows as they progress in time, the dividends that accrue with that kind of instrumentation. And so with respect to the role of information visualization in these kinds of technological enterprises, I think you can think about a couple principal benefits that accrue when you undertake to have this integrated into your workflows. I have a friend who works on the Google crawl team who asks as a thought exercise that you imagine what the structure of your software would look like if it had a physical manifestation. I don't know how many of you have seen Howl's Moving Castle. It's an excellent, excellent movie. And imagine the system of feed belts, and as though the gears of a fine watch that would come together to create the physical structure that is our software. We build these incredibly complex infrastructures that have no physical reality, and in the same way as a software system like this has, I feel that software engineering is a very geometric undertaking. The texture of the high-dimensional data that we work with when we study these social systems is also highly structured. With information visualization, we are able to improve the fidelity of our mental models. And with that improved fidelity comes, I think, the ability to create more innovative products and leverage a deeper understanding of the structure of the data. With respect to the assumptions that you make about the structure of your data as it changes in time, for example, if you have a join step in a workflow, it is often the case that you may be dropping records, or if you think about, you're just making assumptions about your data. For example, how many null values or zeros or ones are in a feature. To the extent that you are able to quickly visualize distributions, you get a perspective on how your data changes as it moves through workflows, so that if at stage A and stage B the structure of the distribution has changed, you can quickly go back and revisit this previous step so as to save time and avoid waiting 10 hours for this job to complete before you realize that your process is flawed. And so this leads to shortened iteration cycles. And I think with respect to these large compute processes, to the extent that you are not waiting an hour and a half for a process to finish to examine text output, it just makes your job so much quicker. And it's really on the margin that we begin to see these efficiencies in teams and at an organizational level. Finally, I think you get out of this process improved predictive performance in being able to investigate the role of outliers in affecting the structure of your models. I mean, for example, I deal with social network data, which is very characterized by long-tail distributions and non-normal distributions. And so many of the models that we use have an assumption of normality built in. And so to the extent that these features do not conform to that assumption, you can really kind of go off the rails with respect to this predictive performance. And so I think that when you visualize the structure of your distributions, just as a matter of course, you begin to see dividends in terms of the metrics that you care about. This leads, of course, to product insights as you understand how people are responding to the different presentation mechanisms that you might have on the site. You're able to inspire new data-driven products or presentations. It's sort of this metrics versus algorithms. And then finally, to the extent that a large part of my job is working with non-technical stakeholders to communicate the algorithmic structure of a data product in a way that is easily understood. And so I think visualizations on an individual level or at the team level can help you collaborate with your peers, either technical peers or non-technical stakeholders. But then additionally, if we're thinking about thought leadership, branding, or just mind share in general, you think about LinkedIn in maps. This is a product that lets you see the structure of your professional network, and visualizations of this character are sticky and are well shared on social media. And so if you have an interesting data set and you can create a visualization that says something revealing about it, I think that this is a very powerful marketing opportunity as well. So I talked a bit about how I'll structure the talk. The first piece here is about hypothesis generation. My PhD work dealt with the question of how social media affects the structure of political communication, specifically with respect to propaganda campaigns, Occupy Wall Street, political polarization. In the course of trying to understand political communication on Twitter, we have a 10% sample of the Twitter data stream. We created this infrastructure that, as a matter of course, when we identify an interesting meme in the feed, visualized time series and network structure data relating to that meme. And so you could imagine a similar infrastructure that just collected summary statistics. But we built out this web interface that produced visualizations for everything that came through our pipeline. And when that's happening as a matter of course, when it's just baked in at a genetic level to your workflow, you begin to see things that give you intuitions for how you might approach a problem that are not immediately obvious from numerical estimates. On the left here, so we're concerned with the question of identifying propaganda campaigns. On the left here, we have a diagram where each point represents a person and an edge is drawn between them if they interact. It's blue if one retweets the other, and orange if they mention one another. Here's the White House. You can see at the center of this cluster, we have the White House account, and all of the accounts giving the White House a piece of their mind. We can see the viral organic structure of the chattering class talking about the White House, so somewhat disjoint from this central ball of users. This has a messy organic structure that is very different from this promotion advertising a nightclub in Las Vegas. And what's unique about this is that we see not only are these accounts targeting many, many other accounts with content, they're also talking to one another to create the appearance of consensus, to make it look as though there's an actual community advocating in support of this menu, when in fact these are all centrally controlled. And so governments and corporations and organizations undertake similar propaganda campaigns to shape the structure of the debate around gun control or foreign policy. And so the question of whether or not we can discriminate between these two classes of communication before these propaganda campaigns have an influence on the political discourse is an important question. What we see when we visualize this data is that the regular structure of the network on your right is quite different from the structure of the network on the left. And so this suggests features such as the skewness of the degree distribution in this network. So the extent to which organic communication is power law distributed. If we observe a network that deviates from that assumption, we may think, okay, this does not belong to the class of typical communication. And so this is an insight.
What does that represent on left and right?
So that's an artifact of the layout algorithm. So that's a single person being retweeted or connecting to many other accounts. Right, so those fans are individuals who are targeting, let's say, 20 other accounts, but then also connecting with the other automated, the other bots in the system. And so this is one way that we might develop an insight into the kinds of features that would discriminate between these two classes of activity, which was our central research objective. But in addition, because we were visualizing every meme that flowed through the system, we began to see other patterns that we were not initially looking for. Here we have several different memes relating to American political communication, and you see that there's this very characteristic bi-clustered structure in these networks. We have two communities of individuals who are preferentially retweeting content produced by other individuals within that same community. They're engaging across the divide in the form of mentions. So it turns out, if we aggregate across all political communication on Twitter relating to American politics, we observe this, we've developed an infrastructure to predict a person's political affiliation. And you see here that these people are, this is the echo chamber, writ large. This is why you're never exposed to information that contradicts your pre-existing belief, because it's so easy to follow people who are more or less like yourself. And they have a strong incentive to, I mean, in pursuit of avoiding cognitive dissonance, they have a strong incentive not to rebroadcast content that contradicts their pre-existing beliefs. And so you're never exposed to credible opposing opinions. They do, however, engage across the partisan divide in the form of cross-ideological mentions. And the problem here is that this is not necessarily a civic discourse. And in fact, exposure to these conflicting opinions may reinforce your pre-existing beliefs. It's like, oh, this guy's kind of an asshole. And that's what's happening. And you can take this lens on a societal process because we have an information stream in Twitter that allows us to very cheaply instrument a phenomenon that is historically prohibitively expensive to study. We are now able to produce insights into the large-scale structure of human communication that are most easily understood through the visual faculties. And then this inspires us to perform statistical analyses that give deeper insight into this process. And so this is an insight that allows us now to make these predictions about people, which then can allow us to look at the policy issues that left-leaning individuals on Twitter are talking about, or the candidates that are on the ascendancy among individuals on the right who have talked about gun control. And so this is the kind of, we can call it a product insight. This was a research program, but it's an insight that was resulting entirely from the process of information visualization. And I mean, this became my PhD thesis. And so this is an example of how you can develop these unexpected intuitions that lead to rather significant outcomes if you undertake to visualize in a latent and frictionless way information as it flows through your system.
What are the yellow lines?
Those are mentions. Mentions, like at mentions. Yeah. So, understanding the texture of high-dimensional data is, I think, essential to the enterprise of machine learning. And I think that it is worthwhile to go through a couple of different characteristic plots that give us a lens on the joint probability mass function. First, I think we'll talk, yes, about this classical set of statistical plots that underscore the absolute need for visualizing statistical data. It may seem like an afterthought. However, like I was saying about these long-tail features, it is not, you can have these four different configurations of points that have identical summary statistics, but whose structure is quite different. And I mean, this is a canonical example in the information visualization literature, and I think it just drives home the point that you cannot trust the numbers alone. And so one of the things that I want to talk about here is the basic pattern that I think characterizes a lot of our work. And this is a simple pattern, but I find it satisfying when I see other practitioners talk about their process, because if someone helps validate, and maybe you just get a little less concerned that you're not doing it right. So we use a Hadoop infrastructure, and what we do is downsample often. So frequently their training data is not so available as to, sorry, all of your Twitter messages are buzzing in my pocket. Gotta do that. Okay. Right. So you will perform some sort of stratified sampling to get a local sample of the data on your machine. For example, we might preferentially favor recruiters, who are an underrepresented segment of the user population, but who are particularly important for a lot of the models that we build. We then take this local sample, and I work in RStudio, and you can perform this interactive feature exploration, where we are plotting in a shell like IPython Notebook or RStudio. It allows us to interrogate the features and perform different transformations on these features, such that we are better able to understand the structure of these distributions. Once you have a lens on the distribution that is satisfying, and you say, okay, I will always want to produce a plot which represents the log of this value plus 1. I put that into something called a visualization. I mean, it's a simple pattern. It's just a file that always runs the same set of plots, a visualization battery. And this will take as input a path to the training data, and it will always create the same 10 plots. And so if I change my sampling procedure, for example, to favor job seekers now, I will want to rerun that visualization battery to make sure that the structure of the distributions has not changed in a way that affects my analysis. And I check these plots into a Git repository, which allows me to back up in time the structure of my distribution, so that if I replot a feature that is maybe not obvious in its computation, or it's not totally transparent, like PageRank is a somewhat difficult computation to debug sometimes, I can go back 3 weeks and say, was this different? I don't have to guess. I can know what it looked like 3 weeks ago and whether or not the structure has changed qualitatively. Similarly, once I perform my modeling work and I've made predictions, I produce a set of plots that are the reference sample for a given, or the reference set of plots for a given model, and I'm able to make comparisons between models using the same outlier detection or receiver operating characteristic plots that allow me to say this model and this model are different in this respect. And so it's this balance between, I'll take my questions at the end, this balance between this interactive, iterative exploration of the data in a shell, and once you set upon a lens on the data that says what you're trying to say, you commit it forever to this battery that you run against every iteration of your data set. And this, I'll do it again. This provides a very consistent visual language in which to understand the structure of your data. So we are often concerned with the structure of a joint probability mass function to reveal the relationship between two variables under study. For example, we might be concerned with multicollinearity, or just how users respond in any regard to a given stimulus. And this holds for all classes of problems. We are often interested in studying the relationship between two variables. And here we have on the x-axis the number of connections a person has, and on the y-axis we have their endorsement, their PageRank in the endorsements network. And we want to understand the relationship between these two features. Obviously, a scatter plot is the first place to start. The problem here, of course, is that there is no way to know that 95% of the mass of this distribution does not exist on that point. That's possible, and this problem of occlusion is very characteristic of scatter plots. And so on the right here, you'll see the ggplot commands for producing these features, or these plots. And what I like is that, especially about ggplot2, is that you can take the same data structure and just apply different lenses on it in this sort of mix and match way. And I think that this is, in some sense, the correct answer to the question of how are you plotting your data. So very simply, we can introduce this alpha parameter, which changes the alpha transparency of each point, such that I have to stack 5 points on top of one another to be perfectly opaque. And this begins to reveal now we think about these probability mass functions in terms of their z-space. This begins to reveal how much of the distribution rests on a given point. And so this is just an estimate of the PMF. And we can see here that there are these horizontal banding patterns. So this reveals maybe some artifacts in the data that we might need to investigate further. The problem with this approach, the scatter plot approach generally, is that it doesn't scale to millions of points. There are new technologies that utilize GPU rendering that can allow you to visualize hundreds of thousands or millions of points. But most, there's a trade-off, because right now these technologies are not necessarily the easiest to use. And so I think that using heat maps, in which color here corresponds to the mass of the distribution in a given bin, this is also a very effective way to interrogate that Z space. The problem, or one of the trade-offs really, is that now those horizontal banding patterns are much harder to detect. And so this is a way to understand, and I think it's an important take-home message, that there is not one true plot. There are multiple different perspectives that tell a convergent story about the data, and it is by toggling between them that you begin to understand the true structure of this distribution. So often in machine learning, we're interested in discriminating between two sets of points. And here we introduce color as a way to represent two different joint distributions. And so here we use experts and non-experts. And we see that experts tend to have slightly more connections and seem to have more PageRank in the endorsements network, but it's difficult to discriminate where these two distributions are separated. And this, I mean, is the essential problem of machine learning, is figuring out where that line lies that discriminates between these two classes. And so a type of plot that I have become enamored of lately is the contour plot. And this is the beauty of ggplot2, is that it's simply a new 16 characters on the same data structure, and it reveals this now totally different plot, where each line is a contour where, along which the value of the PMF is the same. And so you can toggle the number of contour lines to get an increasing resolution on the distribution. And this is, I mean, again, whether you have broad bins or narrow bins, there's not one correct bin width for a given distribution. It's a matter of, do we want large-scale structure, or do we want fine-grained structure, but at the expense of increased noise? And so now we can begin to see in this distribution that a line that cuts through here might optimally separate these two classes. It's a neat trick, and I think quite useful when you're trying to produce a plot that says as many things as possible about the same question. You're always wanting to communicate a single point, to project the marginal histograms onto the axis of the plot. And here this reveals that the two distributions are not especially well separated with respect to connection count, but there is clear separation between these two classes of points with respect to the PageRank and the endorsements network. And so this provides an intuition that one feature might be better than another. There's another tool called gGalley that Hadley Wickham endorses as a better plot matrix functionality. It allows you to see the relationships between many variables at once with respect to a variety of different statistical plots. Here you have different numerical representations of the data. It's something of a power tool. It's tough it requires some tacit understanding of how these plots work to get a sense for what you're looking at, but I think it's quite powerful for small numbers of features. It's worth knowing about. So the next piece of the talk, actually, let's take a beat. Like, I know that you've had a question.
So when you sample this social network data, how to make sure I don't break the social?
Do you want to grab the mic?
Yeah. How do you make sure when you sample the social graph data, don't break the social network? Because traditional data you can sample with ease, but the social network data, what's the caveats?
I mean, it's a very broad class of problems, right? Like how do you correctly get,
Could you repeat the question?
so the question is how do we get a representative sample from a network? And I think that there is not one correct answer. It's very, we are not, suffice to say, we're not technologically constrained. You know, we have very efficient graph databases, and it's not a technological constraint, it's more of a methodological constraint. So it's specific to the problem under study. Like the Twitter data set, for example, it is known because we are trying to take a sampling of a network that reproduces the true population statistics for that network. It is known that edge sampling is an especially bad mechanism for reproducing population statistics. And so with the Twitter data, you're doing exactly that. So instead we might say, well, I'm going to get all of the edges adjacent to an individual. Or I might try to get all of the edges adjacent to high degree individuals. And so I don't think that there's a generic answer to that question, but it's an important problem. You have a question? Okay, so let's keep on rolling. That's a great question, though. So the next piece here is concerned with how we use statistical plots and visualization to understand the structure of statistical models. And here again, we use the same pattern or strategy, which is producing these batteries. And what you'll see is that often, because of this stratified sampling, you'll have different, and I mean, in a sense, many of the